Physics First class. We are going to discuss the idea or the terms of Ohm's law and circuitry, or simple circuits. There's two types of circuits we're going to discuss. We're going to discuss first a series circuit, and then we're going to discuss a parallel circuit. The most simple one is the series circuit, and that's where we're going to do all of our math regarding Ohm's law. And that's where, and as you can see here, this is a series circuit. So in a series circuit, you have your batteries, and then you have your resistors all in a single series. That means in order, in a series. 1, 2, 3, 4. This is what it used to be. So if you ever have seen those movies where people are in a bunker of some sort and they flick on light and then the lights start opening or turning on as they further you get down, bam, 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 bam. That is a series circuit. And in our own school, when you turn a light, they all turn on at one time. Well, that's because they're all receiving it all at one time, and that's called a parallel circuit. So we are obviously using parallels in our school building, and think of the old movies. When something happens, those are going to be series circuits. When we turn it on, and you can see the electricity hitting each one at a time because they're going in a series. Now, things to note for a parallel and series circuit. A series circuit obviously is more primitive, if you want to use that, and so it's less advanced, and so it has more failures. So what are some differences? As you should know, some of the key differences between series and a parallel or a series, they are more dimmer, which means that a parallel is going to be brighter. They also, they're dimmer because each resistor sucks out some of the energy. So less volts to each specific resistor. While the other one, the parallel, has equal volts to all resistors. That's a series. So some of the basics of parallel and series. And one thing that we want you to get is that in a series circuit, if one of these resistors messes up, say I messed up, that one's no longer there. You see the gap there? Well, after this, can electrons cross this anymore? No, it can't. So if this resistor were to mess up like a bulb or something, it would end the circuit for the rest of them, and this would receive no power. So in a parallel series, and let me go ahead and real quickly draw you a simple parallel series. So here I have something that we saw in class all the time. I drew this. I have a battery here. So battery, positive. This is going to be my positive part. A little small lining that represents my anode. And I have a line, and here's my wires. I have my circuit here, and I have another circuit here, so we're going to keep on going. Okay. So this is going to be my parallel circuit. And so as you can see, electrons are going to flow from the negative and go up here. But if there were to be a blowout right here, so this would get messed up. Well, do you see how there's still a circuit? Imagine this is a circuit within a circuit. So this is its own little circuit right here, and this is its own little circuit right there. And so you have basically a circuit within a circuit. So if this one were to mess up, if there were to become a gap right here, and it no longer worked, well, electrons can't cross over. So we got our electrons, and they can't cross over here. So here, whoops, I'm done, can't do anything, so no more electrons getting in. So this one's dead too, sad face. This is dead, sad face. But this over here can keep on flowing through all the way around. So look, happy face. I'm happy I can keep flowing through so I can keep shining the light. The best example of this, of course, is when you're dealing with Christmas lights. So we're all familiar with this. Well, some of us are. As time goes by, we're going to become less familiar with this. That so oftentimes, if you've ever had to fix lights around Christmas time, there's when one of the lights go out in a series circuit, all the other lights. So you spend your time on Christmas trees trying to find that one broken light, the one light that just doesn't work anymore, and it's out. And so then you have to go back and replace that light, so all the other ones can. Well, in a parallel circuit, you don't have to worry about that. If one goes out, you see that that's out, and you change that one, and it doesn't affect the other one. So that's what happens. So that's one of the main differences between a parallel and a series circuit, or one of the effects of a parallel series circuit. Now that we've discussed parallel and series circuits, let's get into some of the nitty-gritty math of these circuits. But in order to do that, we have to first look at some of the essentials of a circuit. So, the long dashes, the long lines of the circuit with two ends on the end, those are called wires, okay? And these wires actually conduct the flow of electricity. So they conduct electrons through here. And again, I want you to, and this is, part of this has to do, to understand why these wires are good at doing this, is you need to understand how metals bond form. Okay, so I told you, remember from the last video, that you have these atoms, and these atoms have these positive regions in the center. Positive regions in the center. That's how a metal, well, that's how an atom looks, right? So imagine circles around there. Well, what happens when metals bond, in all chemical bonding, really, bonds form between different elements or different atoms to form compounds, and they form within the electrons. So in a covalent bond, they share electrons. An ionic bond, they gain or lose to form ions, like those cations and anions that we've discussed. Well, in metallic bonds, they do something different. They actually form something called the electron C model. And you look at this right here. So this is kind of what it looks like if you look in your textbooks. That's kind of an illustration of what you're going to see is the electron C model. And what happens here is that, so imagine it's being copper wire, okay? Let's go back to one of the things that we used recently. Let's go to copper wire. So this is copper wire. And you notice then that I have a pathway of electrons. So right through here, if I had a source, if I had a source of electrons, the electrons have a source. Bam, 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 bam. And they can kind of flow through here any way they want to because they have this range of being able to do so. So electrons, they can flow through here. That's what makes wires and metal such good conductors of electricity, is that this floating electron C model allows it to allows a good pathway, as opposed to rubber, which doesn't allow a pathway for flow of electrons. Water itself, contrary to popular belief, is not actually a good conductor of electricity. It's actually the ions inside of the water that conducts electricity. So keep that to note. Maybe we'll have a quiz. Well, I have a bonus quiz, and I can give you some of these facts, and you can watch these videos and understand it, and you can get some bonus points. So remember, 1, water itself is not a good conductor of electricity. Only the ions inside the water are good conductors of electricity. And wires are a good conductor of electricity because they have that electron C model. Anyway, so now we got back to the wires. The wires are what's conducting the electricity in the first place. So these dashes on this circuit, they are represented by, this is called a diagram. This is an electric circle diagram. And the electrons are actually carrying the charge here. So, or these wires are carrying the flow of electrons through here. Flow of electrons all the way through. I hope that makes sense to everybody. So what are the other symbols that we see here? Okay, some of the things we see here is this little, let's go to this region right here. And let's look at this little dash right here. And if you remember from another video, I kind of drew this too. So this region right here, I have 1, I have a long and a short 2, and I have another long and another short 3. These are the symbols for batteries. Okay, that's what a battery is. I have the long part is positive, and the short part is negative. And do you remember what that's called? This is called the cathode, and this is called the anode, for cation and anion. So this is the cathode, this is the anode. You're going to be asked to be able to draw one of these, so make sure you can, okay? So make sure you're able to draw one of these, a battery, a circuit with a battery. Remember, this is kind of what it looks like. The next thing is the resistors over here. So far, let's have the wires, batteries, and then you have these little dashes, or I'm sorry, squigglies. Those are resistors. And what a resistor is anything that slows down the flow of electrons. And that makes sense. I mean, where are these electrons going to? They're going here. And they drew it squiggly is because it takes longer to get through here, doesn't it? Instead of being a straight line, it has to travel through all the little lines right here, and it takes longer. It resists the flow. That's kind of what the definition of a resistor is, anything that slows down. So as far as we're concerned, a resistor is anything like a light bulb, a buzzer, or anything else that we've used in our lab so far. And we've used specifically light bulbs because we can actually measure them by the brightness. Okay? So in this circuit right here, imagine this circuit, that series circuit I have drawn over here, imagine that I'm dealing with light bulbs. Okay. And then these little dots right here, they represent contact points. It's whenever they come into contact with something that's not a wire. So now here we go. We're dealing. This is a simple circuit with 1, 2, 3 batteries, 1, 2, 3, 4 resistors, and these wires here in between them. Since we've covered the basics, let's go ahead and start doing some mathematical examples using this simple circuit that we have. Before we can move on, we first need to understand the idea of conservation of energy, stating that the energy that's going through here has to be conserved. I have to at least account for it. So when I say energy, I'm referring to electrons. And when I'm referring to electrons, I'm referring to the flow of these electrons. And what is the source of the flow of the electrons? The batteries. So let's look at my batteries. I have 3 12-volt batteries. That means I'm going to have 12, 24, and 36 volts. So leaving this area, this contact point, is 36 volts. 36 volts. And when it hits this point, the moment it hits this point, 36 volts are hitting this point. When it meets this resistor, how much of that 36 is remaining to get to the rest of this? That's our question. So how many volts are hitting here? How many volts are leaving here, which hit here? How many volts are left after this one? How many volts are left after this one? And then finally, we know how many volts are left after this one. It should be 0. But let's make sure we account for these. So how are we going to do that? We are going to use Ohm's law. So here's Ohm's law, and we're going to write down the 3 equations we have for Ohm's law. Okay? The 3 equations are 1, current I equals V over R. So I'm going to go use I equals V. Well, let's make that look prettier. V over I equals V over resistance. So here's my resistance. And remember what the other one would be. Resistance equals voltage divided by current. And then finally, we're going to have current times resistance equals voltage. And these all mean the same thing. It doesn't matter which one I have. It doesn't matter which one I use. These all 3 equations will get me the same thing. Okay? So another way to look at that is the triangle that people are so popular. It's so popular with everybody. So let's look at this triangle. Let's make it a different color real quick. And in this triangle, I'm going to have my voltage. And then I'm going to have my current. Well, messed up there. Voltage there. Let's make that look prettier. Voltage, current, and then resistance. This is the triangle, the same thing as like a density triangle, but it's the same thing. So I have, if I want to know which one I do, how to do this, I just want to write this triangle. What I do is, whichever variable I'm looking for, say I'm looking for V, I cover up the V. So cover up the V with your hand, and V equals I times R. If I'm looking for R, resistance, I cover up my R, and my R is going to be V divided by I. And if I'm looking for my current, it's going to be V divided by R. So, and that just reconfirms these 3 equations right there. So if you want a simple way to write those three equations, you can use this triangle. I hope that part's at least helpful here, guys. And we're going to be referring back to this whenever we're trying to find how much of this is being taken down. So what we need to do first and foremost is we need to first, and in order to do this, follow these steps with me, and please follow along. We're going to first, we need to calculate my total resistance. I'm going to call that R total, and that's my total resistance. And if we remember from class, R total equals my R1 plus my R2 plus my R3, etc., right? Well, how many R's do I have here? I have 4. And so what are they? So my R total is going to be, let's put it at total. It's going to equal 1.6 ohms plus 3.2 ohms plus 6.3 ohms plus 4.7 ohms. Okay, so when we add that up, it's 1.6. I'm doing the math in my head. Well, not on paper, I guess. 6.3 and 4.7. So we look at that. That's going to be 8, 11, 18. 18, 1, 2, 5, 11, 15. So it's going to be 15.8. 15.8. So my total resistance is going to be 15.8. So my R total, I'm going to put that up here for our sakes. R total is going to be equal 15.8 ohms. That's going to be important. So the next thing I need to do after I find my R total is I'm going to have to calculate my current. Now that I have my R total, I'm going to actually have to calculate how much of my current is being affected by this. So let's calculate the current. And of course we know how to calculate current because we just spent the last 3 minutes discussing the triangle. So R total, go back to my green. So how would I calculate current? Which equation do I use? So again, current is I, so I'll cover up the I, and it's going to be V over R. That's why I had to find R total first, right? So I have my total voltage, so I is going to equal, and this is how it needs to be written. I equals V over R, so you write your equation, and then you plug them in. I equals, my voltage is 36 over 15.8. So those in class already know that I'm doing it wrong. And here's the point. It's not 36 divided by 15.8. It's 36 volts divided by 15.8 ohms. Okay? There's no exception. There's no doubt. If you do not have 36 volts divided by 15.8 ohms, it is incorrect. So let's go ahead and do the math on that real quick. 36 divided by 15.8, it's going to get me 2.7 or 2.28. So my current equals, I'm just going to write that in blue. So I equals 2.28 amps all throughout here. So how much electricity is running through here? Well, it's 2.28 amps running through here. So if we remember, that's basically 2.2 times 6.2. So we're looking at 1.2 times 10 to the 19 electrons for every 1 second. That's crazy. So my ampage here is 2.28 amps. Okay, that's all well and good. So what do I do from here? That still doesn't answer my question. How much resistance or how much voltage is being sapped from each resistor? So now that I've calculated my R total and I've calculated my amps, so let's go ahead and write that down for your notes. By the way, if you're watching this video for the first time, you need to be taking notes. If you're watching it for the second time, you need to be reading along with your notes to make sure it makes sense to you. So we calculated current. What next? The last thing we need to do, well, call it the last thing for now, we need to calculate voltage drop. Calculate voltage drop. And here's the caveat. It needs to be for each resistor. For each resistor. Okay? pause out there so you write that down. You can pause it right there to write that information down. Okay, so you have those. That's kind of what we do. Now, when I say calculate voltage drop, how do you do that? How do you calculate voltage? Well, we have an equation that tells us how to calculate voltage. We calculate voltage by, cover up our V. Oh, it's my current times my resistance. And so each one, I have my total current of 2.28, and I have each of those resistance. So for each one, that means I have 4 separate equations. Just plug it in. We're going to magnify this for our sake. Okay, so for our sake, we're going to show the equation one time. I'm going to show the equation one time, and then that should be fine. So the equation is going to be V equals I times R. And this for our sake, V is going to equal 2.28 amps times 1.6 ohms. Agreed? Over here, it's going to be the same thing. So voltage is going to equal 2.28 amps, 2.28 amps times 3.2 ohms. Agreed? Because that's what that is. That's saying 3.2 ohms. That's confusing. Let me put that in parentheses here, because that's what that's saying here. Let me get rid of that little. Come to the next one here. Same thing here. Voltage is going to equal, my V over here is going to, V equals 2.2. Let's move that over a little bit. Don't have enough room right there. My voltage is going to equal 2.28 amps times 6.3 ohms. And then finally, the last one over here, it's going to be V is going to equal 2.28 ohms times, amps, I apologize, amps by 4.7 ohms. Now remember what happens. So what unit should I get for each one of these? So I've got these 4 equations I got to do. What unit should I get for each one? I should get volts for here, here, and here. And when I do all 4 of those voltage drops, I should add up to 36. So the numbers are 1.6, 4.7, 3.2, and 6.3 are 1.6, 3.2, 6.3, and 4.7. Let's go to my calculator app. Okay, so 2.28 divided by 1.6, 2.28 divided by 4.7, I said divided by, I apologize, 2.28 times 1.6, that was because it's V times I times R, equal that one, and then that's 2.28 times, let's bring this up, let's go back to here. Let's make sure we get these numbers written down properly. Let's go ahead and save this if we have a problem here. Okay, so my numbers are 1.6, 3.2, 6.3, 4.7. So 1.6 and times 3.2, that's going to be 2.28 times 6.3, and 2.28 times 4.7. So let's add those numbers up. I've got 3.648, so 3.65, 7 point that. So let's go ahead, well, actually let's make this easier on ourselves and just put it all in one place. So I'm going to put, open parentheses, 2.28 times, please scroll up, 1.6 times 1.6, close parentheses, plus 2.28 times 3.2, close parentheses, plus, open parentheses, 2.28 times 6.3, close parentheses, and last one, 2.28 plus, I apologize, times, don't want to mess it up, 4.7. Let's check our equation, make sure we're right. 2.28 times 1.6 plus 2.28 plus 2.2, close parentheses, plus, okay. Oh, 36.024. And that's kind of what we're looking for. So when we get our answer, it is indeed, when we add all of these up, it is indeed 36.024, or roughly 36 volts. So yes, that's what voltage drop was. If there's any questions, you can ask me to do another video, or we can do some more during tutoring. Thank you.